Hi, welcome to today's talk on vector addition. What are we learning? We're going to do a vector review. We're learning how to add vectors using the tip to tail method. We're going to learn about vector components and adding vectors using these components. The essential question is, how do we add vectors? Let's review vector quantities. A vector quantity is something that has both magnitude and direction. A scalar quantity, on the other hand, only has magnitude but no direction. Scalars are quantities like mass and temperature. They don't have direction. Vectors are things like velocity, and notice how they're notated. They're usually in bold and have an arrow above them. If v is not bold and it doesn't have an arrow on top, it stands for the magnitude of the velocity or the speed. Vectors are represented by arrows. The length of the arrow tells you the magnitude, and the direction tells you the direction. Vectors are equal if they have the same magnitude and the same direction. So in this case, these 1, 2, 3, 4 vectors are equal. Now we're going to learn how to graphically add vectors using what we'll call the tip to tail method. No matter what the quantity is that is a vector, it could be displacement, it could be velocity, it could be acceleration, or now we'll see soon force. When it comes time to add those vectors, we'll do exactly the same thing. A vector is a vector. Now let's say we want to add vector quantity A to vector quantity B. We can't just add the magnitudes up because the resultant of A plus B, which we'll call vector R, is this vector that goes from the tail of A to the tip of B. So R is a sum of A plus B from the tail of A to the tip of B. If we remember from arithmetic, A plus B is the same as B plus A, and we can see that graphically here. This resultant is exactly the same as this resultant. Again, R is the sum of A plus B, and now it's going to go from the tail of B to the tip of A. One way to think about adding vector A to vector B is to pretend like these are displacement vectors. Let's say we start here at the tail of A, and we walk to the right to this point at the end of vector A. This is the displacement vector. Then we take a leftward turn, and we walk up this way to the end of vector B. This is the second displacement vector, B. What is our total displacement? Well, it's this resultant, A plus B. It's from the tail of A to the tip of B. We can add many vectors. We can add A plus B plus C plus D using the same tip to tail method. This resultant is vector A plus vector B plus vector C plus vector D. Now we can draw these vectors to scale and actually measure these out on paper and get a pretty good answer for the resultant vector R. Subtracting a vector is merely adding the negative. Remember, we had vector A and we added vector B. If we were to subtract vector B, we would just add the negative. And notice that negative B has the same magnitude, it's just going in the opposite direction. So this would be A minus B. So adding negative B to A is equivalent to subtracting B from A. And we can write this mathematically, saying that vector A minus vector B is the same as A plus negative B. This is positive B, this is negative B. Multiplying or dividing a vector by a scalar, we merely increase its magnitude by the factor that we're multiplying or dividing. If this is vector A, then 3 times vector A is a vector that has 3 times the length or 3 times the magnitude. And you notice we can multiply by -3. We get the same magnitude, but just the opposite direction. Let's now take a look at vector A drawn on a rectangular coordinate system. Notice that if we draw a horizontal dashed line from the y-axis to the tip of vector A and a vertical line from the tip to the x-axis, we have created projections of the vector onto the x and y axes. These projections are called components. Any vector can be completely described by its components. Much as we saw before, this x component, a sub x, if we add it to the y component, a sub y, we get our original vector. So now that we have the components, we can do a little bit of geometry and just a little bit of trigonometry to find the lengths of the x component and y component of A. We have a right triangle formed with one side being the x component of A and the other side being the magnitude of the y component of A. Going back to trigonometry, if we know this angle theta here, the cosine of theta is the adjacent over the hypotenuse of our right triangle. If we take this equation now and solve it for the x component, we get a sub x is a cosine theta. Much in the same way, the sine of theta is the opposite over the hypotenuse. Sine of theta is a sub y, which is this length here, divided by the magnitude of a. So a sub y is a times the sine of theta. The tangent is the opposite over the adjacent. The opposite over the adjacent. And since this is a right triangle, we can use the Pythagorean theorem to give a relationship between the vector A, its x component, and its y component. So a sub x squared plus a sub y squared is a squared. Solving for a, we take the square root of both sides of this equation, and we get a is the square root of the square of the x component plus the square of the y component. One more trigonometric function shows us, again, the relationship between the y component and the x component and the angle theta. This is the inverse tangent. So if we know the magnitude of the x component and the magnitude of the y component, we can then find our angle theta. Now let's look at adding vectors. We'll call this algebraically, or using the components. We want to take vector A and add it to vector B and get a resultant R. What we can do is take this vector A, split it into its components, the x component and the y component, and then take vector B, split it into its x component and its y component. Then we'll add the two x components and we'll get the x component of the resultant. We add the two y components and we get the resultant's y component. So let's say we're adding vector A plus vector B. Let's split them both into their components. Here's the y component of A and the x component of A. For B, here's the y component of B and the x component of B. We add the two components, the y component of A and the y component of B, and then we add the x component of A plus x component of B. And we get now the resultants x component and the resultant's y component. We can then draw the resultant vector. All right, let's summarize what we know. We can draw vectors. We can add them graphically tip to tail by putting the two vectors tip to tail. The resultant of the vector A plus vector B here, if we start at the tail of A and go to the tip of B, we get the resultant. And if we draw these to scale, we can draw them out on paper and get this resultant just by drawing them. The second way, adding vectors using their components or algebraically, we take two vectors, A and vectors B, we add their y components together, and then we add their x components together to get the resultant. And here we can see that we take the vector A, we're adding it to B, we can add the two x components and get the resultant's x component, and add the two y components and get the resultant's y components. All right, thank you for listening. Rewind and review as necessary, and don't forget your Cornell notes.